All right, ladies and gentlemen, and today we are going to look at the following example or section, set 1.7. In section 1.7, we are dealing with linear inequalities and absolute value inequalities. So let's begin with some notation. And get started with example 1. Here we go. In example 1, we begin, well, first of all, let's look at the notation. Relative to the notation, when we talk about intervals, there is a differentiation between parentheses and brackets. In other notation uses parentheses, which indicates that the extreme values are not inclusive. So we will call this not inclusive. Versus a bracket where we consider this to be inclusive. There are other notations that mean the same thing. Now, I believe that you have been introduced to the open dot versus the closed dot. So open dot on the extremes, on a number line, for example, the open dot is used for non-inclusive, not. The parentheses is the equivalent of this on the number line. So let's say this was a number line continuing. As opposed to its opposite, which is inclusive, in which case we talk about closed dot. And typically we either gesture that the values are between or greater than or less than those values. It depends on the notation itself. So this will be different in either case, sometimes between, sometimes not between, but greater than or less than, that kind of notation. So I don't want you to think that one means one or versus the other. It just depends. Okay. Let's look at possibilities and interval notation versus set builder notation. We call this set builder. And I'm going to give you the graph of each respectively. So if I give you an interval notation that has a parentheses and it has an a comma b as such, in set builder notation, we discuss this as x is a value in the set where a is less than x but less than b, not inclusive. And that is as far as the graph, if you would like, I'll do it this way. This is how the book has it, so you can see the graph right next to it. The graph itself is basically the first graph I drew with two parentheses. And in this case, because x is in between the two extremes, our line is sitting here. Our parentheses are the equivalent of our a and b values, whatever they may be. So this is the a and this is the b. All right. If I give you an interval notation where I have a bracket, then I have a comma b parentheses. Or actually, no, let me give you double bracket first. So double bracket, this is where we started. In set builder notation, you would say that this is x is in a set of values where a is inclusively less than or equal to x, less than or equal to b, and the difference there is the equal to sign. So in this case, here are your a and b values again. Here's a, here's b. However, this time we have a bracket on either end, extreme, indicating that that is one of the solutions, and everything inside of here is a solution as well. You could also have a situation where A is inclusive, B is not, B is exclusive. And in that case, you would still gesture that X is in the set of values where A is inclusive and less than or equal to X, but B is just less than, X is just less than B. So in this case, we're looking at, here's A, here's B. B has the parentheses, A has the bracket. Okay, same thing applies in reverse. So if I say to you, A is exclusive, B is inclusive, and in this case we're saying where X is a value in the set where A is less than X, not inclusive, but X is less than or equal to B, inclusive. In this case, the bracket and the parentheses are simply reversed. That's all you have here. So here's your A, here's your B. The B this time has the bracket because of the equal to sign, and the A gets the parentheses. So these first four are extremely important that you understand them and are able to answer these questions correctly. The fifth example and the sixth example that I have here have to do with infinity. And so this is what we refer to as an infinite interval. By the way, these that I just discussed are closed intervals. These first four that I just introduced. These are closed. Let me just write this here. I'm referring to this grouping right here. These are closed. All right. Infinite intervals. So that has to do with infinity. So for example, infinity never has parentheses. So if I have values of A exclusive to infinity, infinity will always be a parentheses regardless. The notation for this one, if you recall, will be where X is in the set of values where X is greater than A. And you close it out. There's no bracket in this case. And the notation on the number line will simply be that you will have an A. This is a parentheses because it's not inclusive, and the values of A go all the way this way, that way. It's reverse. You could have an inclusive A. So we could have A is inclusive to infinity. In this case, the only difference will be that X is in the set of values where X is greater than or equal to A. That's the only difference. And in this case, we would simply have, again, our bracket, our A with a bracket, and we would be highlighting everything to infinity in this direction. Because if you recall, positive infinity on the number line sits to the right. Here's positive infinity sitting out here. Okay, the next two intervals are similar, except we're dealing with the B value, where we're coming from negative infinity, not inclusive, never is inclusive on the B, all the way to B, not inclusive again. So we have X is in the set of values where X is less than B for this example. And in this case, again, if I have a number line, I'm coming from negative infinity, which is sitting over here, and I'm coming up to the B, not inclusive. So it kind of looks like this if you draw it. All right, same thing with the B. You can also have an inclusive B, but not an inclusive infinity. So you could have negative infinity comma B bracket. Again, the only difference here is that X is a value in the set where X is less than or equal to B. And then we have our notation. Here's the interval where you have negative infinity, and we're going up to the b. This time the b is included. It is inclusive. And we're highlighting from here all the way back. And the last example is when we have all real numbers. So all real numbers. All real numbers means that there is absolutely everything on the number line can be used. There's nothing limiting our equation. And in that case, you basically have two ways you can notate this with set builder. You can either say that x is a real number, or there is also this strange looking r. It's basically like a double, looks like a double notation of r. There you go. In that case, you have negative infinity to positive infinity, and in essence we are saying that all values inside of the number line are inclusive, or are considered as part of the solution. So the notation is extremely important to know. Now they start you off really easy on this example. The first thing that they discuss with you is in example 1, they simply ask you to use interval notation, and this is what they're giving you per question. Okay, so they want you to express, this is the directions, express each interval in set builder notation and then they want you to graph it. So they start you with part A, B, and C. Part A, they ask you to, again, express each interval in set builder and graph. So they give you -1, 4, just like you see it. In part B, they give you 2.5, 4, and in part C, they give you parentheses -4, infinity. And so they give it to you in interval notation. If you notice, this is interval notation. They want you to write it in set builder and then give them the graph. So I'm giving you a little title of each so we can discuss. So in this case, we have set builder where x is a value in the set of values where -1, x is greater than -1, but x is less than or equal to 4. Remember, the 4 is inclusive. And so this is how we discuss, or how we write this out in set builder. When we graph this, remember the number line always starts with negative infinity to positive infinity. So we start with -1. That's a parentheses. And we're going to go all the way up to +4. But that's a bracket. And so we want to highlight everything inside because x is a value within that range, interval. Okay, so for the next one. For the next one, we have set builder notation, where x is a value in the set of values where 2.5, x is greater than or equal to 2.5, but less than or equal to 4. So again, a graph. Here's our graph. We have 2.5 as our extreme and 4. In this case, both are inclusive, so both are brackets, and you're highlighting within. All right. On the last one here, we have a parentheses where, I'm sorry, I'm jumping again. Let's do subbuilder notation first. Subbuilder notation says where x is in a set of values where x is greater than -4. So if you recall in this one, we have our number line. Here's the -4, not inclusive, right? And since it's going to positive infinity, our values are going to be greater than. So we're highlighting to the right towards positive infinity. All right. So I think you should be good with this example. If by chance you want another example, let me at least give you the subbuilder notation part of the try. Go ahead and try this example. So we'll call this D. Go ahead and graph this interval notation. Give me the subbuilder and the graph. Let's call this E, where I have 1, 3.5. Both of these are inclusive, both are brackets. And let's call this F, where this is -infinity, -1, not inclusive on either end. And refer back to these if you need assistance relative to the solutions. Pause this and I'll give you a couple of seconds to try it. Here are the solutions. So for subbuilder, we have where x is in a set of values where x is greater than or equal to -5, but less than 5, not inclusive. And once again, if we were drawing this, here's your number line. Here's your -2, here's your 5. The -2 is inclusive, the 5 is a parentheses, and we're highlighting the values in between. All right. For part E, in this case, both are inclusive, so x is in a set of values from 1, where x is greater than or equal to 1, but less than or equal to 3.5. All right, once again, here's your number line. Here's 1. Here's 3.5. You have a bracket on this side, a bracket on this side, and we're looking at all the values in between here being inclusive. Last example, and in example 1, this is where x is a value where x is less than -1. So in our example here, we draw the number line. Let's pop -1 here. It's not inclusive, and here's -infinity. So we're coming from -infinity to up to the 1, -1, not inclusive. Okay. I'm going to hop over to number 2, example 2. In example 2, we are finding intersections and unions. Of intervals. So we want to use the graph, or we want to use graphs to find each set. Okay, we're going to start with example A, where they give us 1, 4 intersect 2 inclusive, 8 inclusive. So let's begin with that one. And these tend to begin the part of the struggle for some students. What I would suggest you do is let's draw one graph. And in this graph, I'm going to begin in one color. I'm going to use a different color. So let's use orange. For the 1, 4. So here's your 1, 4. So if I were to number them 1, 2, 3, 4, 5, 6, 7, 8. Here's negative infinity. Here's positive infinity. And so 1, 4 are not inclusive. Here's 1, 4 not inclusive. Okay, and let's use a blue color for the 2, 8. The 2 is inclusive. The 8 is inclusive. So now what I want to do is I'm going to highlight all of the 1, 4 in yellow. And I'm going to take, let's go with green. I'm going to use actually no, let's use the light blue. Let's use that to highlight all of the values here between 2 and 8. Now, do you notice that between the 2 and 3, the green and yellow make, or the yellow and blue make the green? So that is your actual answer in this case. Your actual answer is that overlap area where you have 2 inclusive, 4 not inclusive. And so in our case, our answer would be, in this case, that's the intersection. Okay, and this by the way is the symbol for intersection. So when we talk about intersection, we're looking at this symbol, and when we're talking about union, we're talking about this symbol. All right, let's do example or part B. This case they give you 1, 4, but this time they're saying union inclusive 2, 8. And so for this example, I want you to consider again the number line. And we are now looking at the same process. We're still going to diagram accordingly. And so we're going to begin with our 1, 4. So 1, 2, 3, 4, 5, 6, 7, 8. Here's again. Here's our 1, 4 interval. And here's our 2, 8 interval. Here's the 8 over here. Now, the difference here is that this is union. This is not intersection. So understand that I'm going to highlight, in this case, the 1, 4, and then I'm going to highlight again. Notice I'm using a yellow again. This time I'm highlighting with the same color because union indicates everything. So our answer for this one should simply be parentheses 1 not inclusive, 8 inclusive, because it's union. And that's our answer for this one, respectively. Okay, now examples to try. You're going to pause the video, and I'm going to give you 2 more values to try, which I'm going to call C and D. So here's C. In C, we're going to give you 1, 3 inclusive, intersect 2, 6 exclusive. Okay, and in D, I want to give you this one where I have 1, 3 inclusive, union 2 comma 6 exclusive, so nothing changes except for union. So pause the video, and here's a solution. The solution is you're going to have 1 comma 6 not inclusive. That's the answer for the last one. And for this part C, your answer should be 2 comma 3 inclusive. All right. I'm going to do example 3 next. Example 3. We are going to solve. So basically solving a linear inequality. So it says solve and graph the solution set on a number line. Apparently this morning is challenging for spelling number line. There we go. They give you 3 minus 2x less than or equal to 11. So what I'm going to remind you of is the rule that if you ever multiply or divide by a negative, you have to reverse the inequality. Now, as far as this first step, first thing you're going to do is you're going to subtract that 3 on both sides. No questions asked. So that means that you have negative 2x is less than or equal to 8. However, at this step, I'm going to divide by negative 2 on both sides. And this gives you x is greater than or equal to negative 4. And so what they're going to ask you in this case, now that we solved it, is we're now going to graph it. So here's our number line. Here's negative infinity. Here's positive infinity. Here's negative 4. This is inclusive, so I've got a bracket, not a parentheses, and I'm highlighting to the right of this. And there you are. That's all they're asking you to do. So I would like for you, if you understood that, to show me that you do by doing this try question. So here's your try. And your try question, I'm going to give you same directions. This is just going to be negative 2x minus 4 is greater than x plus 5. So go ahead and give that a shot. My apologies, this is actually example 4. The try question is actually 2 minus 3x is less than or equal to 5. There you are. Okay, pause the video. I'm going to give you the solution. Your solution should be negative 1 comma infinity. For interval notation, for stability, you should have where x is in a set of values where x is greater than or equal to negative 1. All right, sorry about that. Here's example 4. We are solving a linear inequality. And they're giving you negative 2x minus 4 is greater than x plus 5. In this question, understand that we're just going to have to move the x's to one side and all the numbers to the other. So in essence, my first step will be to subtract x on both sides. You can subtract all day long, doesn't matter, it's not going to change your value. This gives you negative 3x is greater than x plus 5. I'm sorry, 3x minus 4. Wow, We're having a morning today. Let's try this again. This is going to leave us with negative 3x minus 4 is greater than 5. There you go. Okay, next step, we're going to add that 4 to both sides of the equation. That puts us at negative 3x is greater than 9. And the last thing is to remember, again, I'm dividing by negative 3 on both sides. So that means that x is actually going to be less than negative 3. Not inclusive. So if I'm thinking of this as a graph, first of all, in set builder notation, this would be x is in the set of values, or x is less than negative 3. Interval notation, this would be negative infinity to negative 3, not inclusive. So remember, this is set builder, this is interval notation. Our graph in this case will look like this. Here's negative 3, negative 4, negative 5, actually negative infinity sitting here. And so in essence, not inclusive, so it's a parentheses, and we are graphing on the left side this time, heading in that direction. All right. I may have time for example 5, so let me continue in this case. Example 5. In this case, we simply are solving a linear inequality containing fractions. And so they're giving you x plus 3 over 4 greater than or equal to x minus 2 over 3 plus 1/4. Now the first thing I'm thinking of is to get rid of the denominator, which should always be your first strategy in most cases. So in this case, I'm going to take the whole equation, I'm going to multiply by 12 over 1 to get rid of the denominators, and what that gives me in this case is I end up with 3 times x plus 3 is greater than or equal to, this will become 4 parentheses x minus 2, and then lastly plus 3. If you didn't catch the math, 4 goes into 12 3 times, so they have 3 times this. 3 goes into 12 on this equation, where this becomes 4. And over here, 4 goes into 12 again 3 times, so hence 3 times the 1. That's where the math is coming from. So if I distribute the 3 to both of these values, I distribute the 4 to both of those values, I end up with 3x plus 9 is greater than or equal to 4x minus 5, because this will become negative 8 plus 3, hence why I said immediately I just jumped to negative 5. So all of this becomes negative 5. Now in this case, as always, we're still going to move everything that's a number to one side. So perhaps in this case I could subtract the 4x first. So let's subtract the 4x and bring it over here, and I'll subtract the 9 and bring it over here. Always the opposite operation. So that means that I'm left in this case with negative x is greater than or equal to negative 14. But I need to get rid of that negative, so I'm multiplying both sides by negative 1, making this positive x is less than or equal to positive 14. And so again, in set builder notation and interval notation. In set builder notation, I have where x is in the value, x is less than or equal to 14. In interval notation, I have not inclusive, negative infinity, comma, positive 14, inclusive. As far as we see the number line, here's a number line. Here's 14, it is inclusive. And x is the value is less than that. So we're going to highlight all the way down as such. Okay, I'm going to pause the video here just to make sure that we have enough bandwidth to keep it going. And I'll continue examples 6 to 11 on another slide.